we present our paper called Toward Planet-Wide Traffic Camera Calibration. As of 2016, there are approximately 350 million CCTV cameras in the world. With a simple YouTube search, we can access many publicly available video streams like this all around the world. There are many use cases for traffic cameras, such as vehicle speed measurement, automated traffic analytics, detecting the frequency of near miss or near accident, as well as a few other applications for improving urban planning. Then the question becomes, how to turn any traffic camera into a smart camera? We argue that for many of these applications, 2D information such as detection or segmentation alone is not enough. We need to be able to extract 3D information from these traffic cameras. However, there's one important challenge. Camera calibration is not known. Consider this video stream where beside the video itself, we don't know any of this information such as the height, mounting orientation, field of view, or distortion parameters. In other words, we don't know either the intrinsic or extrinsic parameters of the camera, and this is a crucial limitation to enable 3D related applications. Given a single RGB video, there have been many approaches to obtain camera calibration. Firstly, there are manual approaches where we use measurements such as checkerboard or known distances on the road. However, these methods are impractical, especially if we don't have access to the physical location. On the other hand, automatic approaches have tried to detect orthogonal vanishing points, such as lane markings or vehicle motion, or learn a network to regress camera calibration parameters, or use known dimensions such as vehicle size to obtain the metric scene scale. However, these methods are usually not accurate enough and do not work well on our distribution data, such as traffic camera viewpoints. In our approach, we leverage a large source of street-level imagery, in this case Google Street View. Note that their coverage is extremely dense, and in our paper, we show that this untapped rich data source can be very useful for accurate traffic camera calibration. At each location, we can query the closest panoramas that come with their GPS coordinates. In terms of technical method, we follow a standard structure for motion and localization pipeline. First, using street view panoramas, we perform 3D scene reconstruction to obtain an up-to-scale 3D model. The GPS coordinates of the panoramas are then utilized to get metric scale. Next, given a query image from one of the traffic camera streams, we perform camera localization to obtain the extrinsics as well as the intrinsic with respect to the 3D reconstruction that we just built. Given panorama images, we first perform perspective projection to extract perfectly pinhole perspective images with known intrinsics. For these images, we mask out potential dynamic objects such as pedestrians or vehicles so that only the features from the static background are considered. Next, we use a learn feature extractor superpoint and perform feature matching using superglue. Instead of matching exhaustively, we use a simple visual similarity module to retrieve the most relevant image pairs for matching. After this, we run structure for motion with panoramic constraint to obtain the 3D reconstruction. Then GPS coordinates are used to obtain the correct metric scale. After obtaining the 3D reconstruction, we want to localize the query image from a traffic camera stream. We follow a standard camera localization pipeline. Initially, we extract superpoint features, followed by matching these features with the most relevant image pairs from Google Street View used in the 3D reconstruction step. Subsequently, the correspondences are used in the PNP and ransack process, followed by a few bundle adjustment iterations to refine both the intrinsic and the extrinsics. One important technical detail is that we should enforce known relative pose between frames sampled from the same panorama. For example, in this case, we uniformly sample and extract perspective images from the panorama along the yaw direction, using them as input to our 3D reconstruction method. Enforcing this constraint in the bundle adjustment step is crucial. Otherwise, the recovered viewpoints in red belonging to the same panorama may not coincide with each other. After enforcing this panoramic constraint, we can obtain better 3D reconstruction, therefore better camera calibration and localization. We also show quantitatively that by enforcing this constraint, we can significantly improve camera calibration accuracy, especially when the number of images being used for reconstruction is limited. This can be crucial when dealing with the limited number of Google Street View images at a location or when computational efficiency is a priority. In this example, we show 7 localized cameras at an intersection where we show the 3D reconstruction, ground plane, as well as 7 localized cameras visualized in red. Observe the accurate localizations of the cameras. Additionally, we show the traffic camera on the left and the 3D reconstruction on the right. The localized traffic camera frustum is visualized in red. Observe that, using our estimated camera parameters, the render image from a 3D reconstruction is well aligned with the real traffic camera image. In another example, even in a location that is currently challenging to access physically, such as Ukraine, we can still obtain accurate camera calibration parameters. Currently, we were able to scale our method to more than 100 localized cameras across multiple continents, with the potential to scale to any camera with sufficient street-level images. Here, we show a few examples with the localized traffic cameras in red. For quantitative evaluation, we propose a new dataset called Calibrated Urban Traffic Cameras. It contains 20 cameras across 6 diverse locations. They are fully calibrated, and it contains manually measured distances on the road plane that can be used for evaluating distance measurements. Quantitatively, our method outperforms state-of-the-art methods in terms of intrinsic parameters estimation, including focal length, principal points, and distortion coefficients. Additionally, our method is also better in terms of estimating distances on the ground plane, showing the accurate calibration. As an application, accurate camera calibration information allows us to perform 3D downstream tasks with high accuracy. Here, we show an example of 3D vehicle reconstruction visualized on top of the 3D reconstructed scene with the camera frustum visualized in red. Using 3D vehicle reconstruction from the previous step, we show another application which is speed estimation and analysis. Here, we show the image from the camera with the speed trap visualized in green as well as the vehicle activity heat map. Next, we show a histogram of the vehicle speed when the car crosses the speed trap. Looking at this histogram, we can analyze many specific vehicle patterns for this location, such as slow turn into the gas station. The cars are moving slowly due to traffic. The car is moving at normal speed. Or there's an emergency vehicle on duty. This allows us to automatically extract insights from the data that could potentially help improve urban planning. In conclusion, we developed a scalable framework for precise global traffic camera calibration using street-level imagery, localizing over 100 cameras. We also introduced a novel dataset of 20 fully calibrated traffic cameras useful for future research. Finally, we demonstrated an application in traffic analysis through 3D vehicle reconstruction and speed measurement, enabling further smart cities applications. Thank you for listening. Please visit our webpage for more information.